So, in this class, we'll discuss about objective bits of second unit 2. See, objective bits. So, what is your syllabus? Working principles of all machines. So, what is the working principle of DC machine? What is the working principle of DC machine? North pole, south pole. Means how you are getting north pole and south pole? If you place field winding, and always give the DC supply to field winding. Always give DC supply to field winding. So which type of supply given field winding always? Field winding supply is DC. Supply is DC. Always. Always field winding supply is DC. So whenever the DC supply given to the field winding, what happen? North and south poles are created. North and south poles are created. So here coming to DC machine. In DC generator, what happen? Rotating conductor is placed. So that what happen? EMF is induced. Rotating conductor is placed. This is rotating conductor. EMF is induced. Okay. That induced EMF is always AC. Induced EMF is always AC. Always AC. Okay. But coming to DC motor, this is for generator. For DC motor, which type of conductor is placed? Which type of conductor is placed? Field winding is same. Here you will give DC supply. So here input is electrical. How you will give electrical? Through brushes and commutator. You will give DC supply. So you are giving DC supply. But what is the function of commutator? Which is converting from DC to AC. So which type of current passes through the conductor? AC. So always AC current passes through the armature conductor. Here also always EMF is AC. How you are getting DC here? Using commutator. So which type of supply you are getting? DC. Means here EMF induced in the coil is AC. But what you are getting? Result is DC. So here what is the function of commutator? Commutator converts from AC to DC. What is the function of commutator? What is the function of commutator? In generator, which is converting from AC to DC. In motor, which is converting from DC to AC. But the EMF induced in the coil is always AC. So, what is the function of commutator? In generator, converting from AC to DC. In motor, converting from DC to AC. Okay. So these are the working principles of generator and motor. So these are the important bits. Field winding, always you will give DC supply. EMF induced in the coil is always AC. Commutator function in generator, which converts from AC to DC. In motor, which is converting from DC to AC. So coming to which type of EMF is induced in generator? Dynamically induced EMF. Why? Because it is moving. It is rotating. If it is moving, which type of EMF is induced in the conductor? Dynamically induced EMF. If conductor is moving, in moving conductor, induced EMF is called moving conductor. Induced EMF is called dynamically induced EMF. Dynamically induced EMF. Dynamically induced EMF. What are the examples? DC generator, DC generator, induction generator, and synchronous generator. All rotating generators produce dynamically induced EMF only. Dynamically induced EMF only. Dynamically induced EMF only. But coming to transformers, here, which type of supply you are giving? AC supply. Which type of current? AC current passes through the coil. So that magnetic field is developed. That magnetic time varying magnetic field cuts to the coil, so that EMF is induced. Which type of EMF is induced? This EMF is statically induced EMF. Statically induced EMF. Statically induced EMF. Why it is statically induced EMF? Because conductors are stationary. Because conductors are stationary. So in transformer, which type of EMF is induced? Statically induced EMF. Statically induced EMF. But all rotating generators, which type of EMF is induced? In all rotating generators, which type of EMF is induced? Dynamically induced EMF. Dynamically induced EMF. Dynamically induced EMF. Dynamically induced EMF. So these are the conclusions. So in all rotating generators, which may be DC generator, synchronous generator, or induction generator, EMF induced in the coil is dynamically induced EMF. Dynamically induced EMF. Is it clear? If there is having rotating part. Okay. But the EMF induced in the transformer coil is statically induced EMF. Statically induced EMF. Okay. See, compare with all machines. Which one is giving more efficiency? Efficiency is nothing but output by input. Input is nothing but output plus losses. Which losses? Which losses? Which losses? Losses are nothing but which may be combination and electrical and mechanical losses. But in transformer, is there any mechanical loss? If there is having rotation, there is having mechanical losses. If there is having rotating parts, then only there exist mechanical losses. Mechanical loss, friction and windage losses. But in transformer, friction and windage losses are zero. Friction and windage losses are zero. So there is no mechanical loss in transformer. But remaining all machines, all are rotating machines. So that there exist mechanical loss also. So in which case efficiency is more? In which case efficiency is more? Transformer. So efficiency of the transformer is greater than all rotating machines. All rotating machines. All rotating machines. All rotating machines. Is it clear? Right. So from this, what you are giving, what you can give the conclusion? What you can give the conclusion? Field winding supply is always DC. EMF induced in the conductor is always AC. Commutator, which converts from AC to DC in generator, DC to AC in motor. And EMF induced in the transformer is statically induced EMF. EMF induced in the generator is dynamically induced EMF. And what is the efficiency of the transformer? In which type of machine efficiency is more? Compare with all rotating machines, transformer efficiency is more. Why? Because there is no mechanical losses. along with electrical loss are also less. So coming to synchronous generator. Synchronous generator. So what is the working principle? What is the working principle? Here, field winding placed on rotor and armature winding placed on stator. This is R, Y phase, B phase. So what happened whenever the DC supply given to the coil field winding, what happened? North and south poles are created. But here north and south poles are, this is constant magnetic field. Magnetic field is constant. Conductors are also, armature conductors are also constant. So can you get any EMF in the armature winding? No. Why? Because both are stationary. That's what you should rotate the rotor in clockwise. If it is rotating, what happen? North pole first cuts R phase, after that cuts Y phase, after that cuts B phase. Means north pole, if north pole is rotating, flux cuts to the phase is also changing. So first more amount of EMF is induced here, after that more amount of EMF is induced here, after that here more amount of EMF is induced. Means here, see, in synchronous generator, the rotating magnetic field cuts to the rotating magnetic field cuts to the conductor, so that EMF is induced. EMF is induced in armature conductors. So here what is the matter? Synchronous means maximum speed. Synchronous speed. Rotor is rotating with synchronous speed. Maximum speed. But coming to synchronous motor, in synchronous motor also rotor is rotating with synchronous speed. But coming to induction motor, stator is same, R phase, Y phase, B phase. Stator is same. But rotor, this one is R phase, Y phase, B phase. Rotor. Here field winding is placed on rotor, but here again three phase winding is placed on rotor. That is induction machine. But in induction, what is the difference between induction motor and induction generator? Here rotor speed is less than synchronous speed in induction motor. But in a induction generator, rotor speed is greater than synchronous speed. But here rotor speed is equals to synchronous speed. That is the difference. See, here synchronous motor, rotor speed is equals to synchronous speed. But in induction motor, rotor speed is less than synchronous speed. In induction generator, rotor speed is greater than synchronous speed. So what are the important bits here? Synchronous generator. Here also field winding is always placed on, field winding is always exciting with DC. So field winding exciting with DC. Understand? EMF induced in the armature coil. Whenever the magnetic field is rotating magnetic field cuts to the coil, EMF is induced. Okay? But coming to induction machine. In induction motor, rotor is less than the synchronous speed. Rotor is rotating with less than the synchronous speed. In induction generator, rotor is rotating with more than synchronous speed. Clear? So these are the some important bits in second unit. Along with we'll discuss working principle of PMMC, PMMC and moving iron. Already you know very well. Same working principle of DC motor is used here as per diarsenal galvanometer. Here working principle is used. So what is the working principle of DC motor? Whenever the current carrying conductor is placed in constant magnetic field, what happen? Torque will be developed. Force will be developed. Due to that force will be developed. So what is the means? Due to that force, what happen? Spindle will move. Spindle will move. So initially spindle is deflecting. So what is the torque developed initially? Deflecting torque. What is the torque developed initially? Deflecting torque. Due to deflecting torque, spindle is moving. Due to deflecting torque, here I will connect the spindle. So when the spindle is moving, due to torque, see, whenever the current carrying conductor is placed in constant magnetic field, what happened? Torque will be developed in the conductor. Due to the torque, conductor is moving. Means if the spindle is connected to conductor, if conductor is moving, spindle will also move. Understand? So spindle is deflecting, moving, deflecting. So deflecting torque is developed. So due to the deflecting torque, spindle is moving. But suppose if I apply uh, 10 volts, spindle should stop at 10 volts. Okay, when it will stop? If there is having controlling force. When you will, how you will provide controlling force? By using spring. So controlling torque provided by controlling torque means opposite to that of deflecting torque. Here spindle is moving, this is deflection. Spring is providing opposite force. Opposite force is nothing but controlling torque. So controlling torque provided by spring. Deflecting torque provided by supply. So whenever the supply given to the conductor, what happen? Current carrying conductor is placed in constant magnetic field, so that torque will be developed. Due to that torque, spindle is moving. Understand? So deflecting torque due to that is called deflecting torque. Understand? How the control torque is developed? Due to spring. Okay. So you can overcome the damping. So due to deflection and controlling torques, this is deflection, opposite torque, controlling torque. Due to these torques, what happened? There is having some damping torque developed. This can be overcome by using some air chamber in moving iron. There I will use air chamber. Okay, so that is damping torques. At steady state, deflecting torque is equals to controlling torque. Why? Because damping is nullified. So that deflecting torque is equals to controlling torque. So at steady state, deflecting torque is equals to controlling torque. See here in PMMC, deflecting torque is directly proportional to current. But in moving iron, deflecting torque is directly proportional to I square times of current. Controlling torque is directly proportional to theta. Here also controlling torque is directly proportional to theta. But at steady state, both are same. So that theta is directly proportional to I in PMMC. Here theta is directly proportional to I square. These relations are very, very important. Here deflection is linear. Here deflection is non-linear. Why? Because square times. Understand? At steady state, both are same. Controlling torque and deflecting torque. So here, what are the important? Here, deflecting torque can be obtained by supply. Initially, if you give the supply, what happen? Deflection you will get. But that deflection can be controlled by spring. Controlling torque is provided by spring. Okay. Next, due to these two torques, some damping will be present in the system that can be overcome by using air chamber. But at steady state, after nullifying the damping, what happened? Both deflecting and controlling torques are same. So this is at steady state. Means deflection is directly proportional to current in PMMC. Here directly proportional to I square. Here directly proportional to I square. So PMMC is linear, moving iron is non-linear. So these are generally used in voltmeter and ammeter. So PMMC is suitable for DC. Moving iron is suitable for both DC and AC. These are important bits. This is about second unit. Thank you. Next, we will discuss about third unit objective bits.